All right, let's talk about some of the RF magic. I think you're familiar with filters that maybe look something like this. This is a 2800 megahertz low-pass filter. And here's a fancy one. This is a 2 megahertz, 2 gigahertz low-pass filter. It's got these bow ties on it. That's kind of cool. And let's go ahead and see what it looks like here. All right, it's got a very nice pass band. And if we set our marker to 2 gigahertz, there's our marker right there. So it's right on the design spec. So it is a low-pass 2 gigahertz filter. And it's attenuating down to minus 40 dB. So yeah, pretty nice filter. Very sharp cutoff. And that sharp cutoff has to do with how many orders is the filter, right? If it wasn't very many orders, it would roll off slowly. And we can kind of see, just kind of in generalities, there's lots of things going on here, and there's only a couple things going on here. So this is probably a higher order filter than this one, right? Let's go ahead and put this one on. I think I can just barely see this one on this 3.2 gigahertz analyzer. This one is a 2.8 gigahertz filter of not as good of quality, lower order. Yeah, we can just barely see it now. You can see it kind of sneaking in right there. Let's do a marker at 2.8 gigahertz. And so this filter is off the design spec, right? It's actually more like a 3 gigahertz filter. So they missed their design mark. It will pass 2.8, but it's not attenuating until up to around 3 gigahertz. So I should probably mark this one. And a little bit of lumpies in here, but basically, you know, again, it's a low pass filter. All right, what about these types of filters? These are solid copper on the bottom. So there's like a ground plane under there, right? So we have this ground plane. And then there's material over that ground plane. And then we have these metal areas. So we have this kind of like this fan-shaped, oops, I'm on that camera, there's fan-shaped things. So we kind of have a fan-shaped thing here, and then maybe a little bit bigger one here, and one here, and one here, and then a small one again, all right? And then these are connected. Well, it's like having capacitors. These act as capacitors to this ground, right? And then we have this wire that kind of comes through. And if you think of these narrow bits as inductors, now it's a CL. It is like a shunt first low-pass filter. And we can take a look at whether that makes sense or not. What about this guy here? Well, he's in little narrower things, okay? And we needed more inductance because it's a lower frequency. We needed to throw away more frequencies. And so this needs to be a bigger inductor. And so that's why the wire here in the middle is thin. The trace here in the middle is thin. And then we have two things. Well, it's just bigger capacitors. It's like having a capacitor to ground, and then an inductor, and then a capacitor to ground, and then we said, oh, we needed more. So we put over here, we put another capacitor to ground, and here we put a capacitor to ground, okay? And so these capacitors are just in parallel with one another, and so it's double the capacitance. So that's the only thing going on here, is that we just needed more capacitance because, once again, we needed a lower frequency. And so big capacitors, and big big value inductor, right? So this fine wire is big value, a large value inductance, and a large value of capacitance. So your L's and your C's are bigger, which means that your frequency goes down. So that's the way this is 2 gigahertz. All right? So it's a whole bunch of those. Now, what order is it? Well, it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's probably a 13th order filter. And we can see what that would look like on a model. But that's basically the way these things are operating. Now, there's more to it than that. I really don't want to get into it for this series that I'm doing, but inductors are basically creating a high impedance path, right? The inductors won't let through high frequencies. They'll reflect back the high frequency. In a resistive divider, the power gets killed in ohms wattage, right? If we shunt something to ground, then that power can go into the ground. But the high frequency here gets shoved back, and it goes back to the source. So any power that's input to this thing, if it's not in its passband, it actually gets reflected back to the source. The source has the option of reusing it and sending it back again, or the source has the option of creating heat there. But it's up to the source to take that energy, not the filter itself. Now, so you can think of these as either inductors, okay? So a high value inductance reflects back more power, or in transmission line theory, let's say you have an antenna, you have a 50 ohm system, but your antenna is 100 ohms. Well, you have an SWR of 2 to 1, and it will reflect back the power because there's an impedance mismatch. And if you're in impedance here, there's 1,000 ohms, then a whole bunch gets reflected back, right? And so it has more to do with impedances than it does with inductors. And in order to design these correctly, you really need CAD models to do all the Maxwell's equations in 3 dimensions and takes into account all kinds of stuff. But in first order, it's just this. It's just an LCs, where these are all the C's and these are all the L's. And it should look very, very common as a type of filter. And then you can just read the number of inductors and read the number of capacitors and say it's a particular order filter. And this one's going to have a sharper fall off than this one. And they basically will act like lumped filters made out of just inductors and capacitors. They're just different. Now, why do they have this funny shape? One of the reasons is that you want to have a length here. So you don't want to hang a big fat thing on the wire here because that'll screw up your transmission line. So you want to just contact it at a little point here, and then this gives you a bigger area. There's also a broadening of the region that it works well over by having these shapes and stuff. And the shapes can be used for various reasons. It's very complicated. It's hard to find books that actually talk about things very well. I'll try to talk about some other designs in Microstrip designs. We'll take a look at those. There's all kinds of different shapes and sizes and reasons why things do certain things and reasons that things don't do certain things. Just as a teaser, I'm going to show this filter here. This is a filter that I actually designed and manufactured. It is a 2.4 gigahertz center. It is a bandpass filter. It's 225 megahertz wide bandwidth. It's what's called a hairpin filter. And this uses an entirely different principle. And it is like, these are like little quarter wave antennas. And the RF energy comes in and it starts to find this distance. And it says, oh, I can oscillate on that distance. It's like an antenna to me. And so its signal strength is going to be big. And if they put an antenna right next to it, then they couple the energy across it. It says, oh, I can transfer my energy from one side to the other just fine. And so I'm going to transfer my energy, and the most amount of energy I can transfer is this quarter wavelength. And then I'm going to do that again, I'm going to do that again, I'm going to do that again, and that will increase the order of the filter, and it will make the bandpass narrower and narrower and narrower, depending on how many of these hairpins you have in it. I'll put a link down below. I did a whole series on me modeling this in Keysight software that does three-dimensional Maxwell's equations, and then I modeled it. I went to PCBWay and had it built on Rogers material. This is a really expensive material. It's not regular PC board material. It's a ceramic type material, gold plated, and they came out really, really good. I was really pleased with this project that I did.